In this lesson, we're going to talk about a different type of derivation than all the ones we've looked at so far. This is doing a derivation to prove a theorem rather than the conclusion of an argument. Theorem is just another name for a logically true sentence. They're called theorems because they can be proven true in our logical system in their own right, meaning without any premises. So when you're asked to prove a theorem, you'll just be given the symbolized sentences to derive. With sentential logic, this means you'll always be starting line 1 with an assumption for a subderivation. What assumption you use and what subderivation rule you're using will depend on the structure of the theorem you're trying to derive. Let's look at some examples to explain what I mean by that. So the first theorem we're looking at is it's not the case that P and not P. Setting up our derivation will just involve creating our main scope line, since we don't have any premises. Right from line 1, we'll be using our derivation rules. So what subderivation rule should we use, and what should we assume for it? The theorem we're trying to get here has a negation as its main connective. So the strategy I'm going to take is assuming the sentence without that negation for negation introduction. So now we have P and it's not the case that P, and what we're trying to get inside this derivation is a contradiction so that we can get back to the main scope line. For this problem, that contradiction is easy. We can get P on line 2 by conjunction elimination from line 1, and we can get it's not the case that P on line 3 using the same rule, conjunction elimination from line 1. So now we've shown that the conjunction P and not P gives us a contradiction. So we can get it's not the case that P and not P on our main scope line by negation introduction from lines 1 through 3. That problem is fairly straightforward, so let's look at another one. Here what we're trying to prove is Q or it's not the case that Q. We have to decide what strategy we want to take. You might think that since this is a disjunction, we should aim at using disjunction introduction. However, to do that, we have to do something first because we have to get either Q or it's not the case that Q by itself. I don't see a way to do that directly, so we need to try a different strategy to start. We're going to use the strategy I always recommend when we don't see another way to get what we want, by assuming the opposite. Since Q or not Q doesn't have a negation as the main connective, we're going to add a negation over the whole sentence and assume it as a premise for negation elimination. So now we need to get a contradiction, but the negated disjunction doesn't give us a lot to work with by itself. So now I'm going to try that strategy we mentioned earlier of getting either Q or not Q by itself, so we can use disjunction introduction like we talked about. This can be done a couple of ways, but what I'm going to do is assume Q for negation introduction. Now on line 3, we can get Q or not Q using disjunction introduction from Q on line 2. Now we have enough to get the contradiction. We just need to reiterate from line 1. With that contradiction, we can get it's not the case that Q on the scope line of our first subderivation by using negation introduction, citing that second subderivation from lines 2 through 4. Now we have enough to use disjunction introduction again to get Q or not Q at this level on line 6. Our assumption here was it's not the case that Q or not Q, and now we've proven Q or not Q follows from it on line 6. Let me reiterate from line 1 to make the contradiction clear. So now we've done all of this to show that assuming the negation of Q or not Q leads to a contradiction. So on line 8, on our main scope line, we can get Q or not Q from negation elimination from lines 1 through 7. This fairly simple looking theorem that a sentence is either true or false took some work to prove. It's pretty common to use negation introduction and elimination to prove theorems like we've done in these last 2 examples. But let's look at a couple of problems that can be solved with other subderivations. other subderivation rules. The theorem we're trying to prove here is a biconditional. When you see one like this, a good strategy is to use biconditional introduction. So I'm going to start by assuming the left side, G and H, for biconditional introduction. Now we need to get H and G. We don't have any quick shortcuts yet for moving around the order of conjuncts, so we need to take the conjunction apart and then reintroduce it in the order we want. So line 2, we get G by conjunction elimination from line 1. We get H by the same rule on line 3. And now on line 4, we can use conjunction introduction to get H and G. I want to note here, it doesn't matter what order you take those conjuncts out in, which one comes first in the derivation. When doing conjunction introduction, you can put them together in any order you like. So now we've proven H and G from G and H. To get the biconditional, we need to do the second independent subderivation, proving G and H from H and G. And now we're going to do this the same exact way we did the first one. Conjunction elimination to get the conjuncts, and then conjunction introduction with G and H in the order we want to finish this proof. Now we've done the two subderivations to prove that that relationship is symmetrical. So we can use biconditional elimination on line 9 to get G and H if and only if H and G on the main scope line. Let's look at one more problem. Here we need to prove that if it's not the case that A or B, then it's not the case that A and it's not the case that B. Here our main connective is the material conditional. So we're going to assume the antecedent that it's not the case that A or B for conditional introduction. Now we need to get it's not the case that A and it's not the case that B. Since that consequent is a conjunction, I'm going to plan to get each of the conjuncts on their own and then use conjunction introduction at the end. So how can we get it's not the case that A? We don't have enough here to get it directly, so I'm going to assume A for negation introduction. Now we need a contradiction, and we need to get it using the inference rules and the two assumptions we have so far. Since we have A, I'm going to get A or B on line 3 by disjunction introduction from line 2. Now you can see our contradiction, but we need to have the whole contradiction inside the subderivation. So we need to reiterate from line 1 to be able to do that negation introduction. On line 5, we can move back a scope line and put it is not the case that A by negation introduction from lines 2 through 4. Now we need to get the other conjunct of our consequent, it's not the case that B. To do that, I'm going to repeat the process we used to get the negation of A. On line 6, we assume B for negation introduction. On line 7, we use disjunction introduction to get A or B. And then on line 8, we reiterate from line 1 to create the contradiction. So on line 9, we can discharge the premise and close the subderivation to get it's not the case that B by negation introduction from lines 6 through 8. Now we have against the first subderivation scope line, it's not the case that A on line 5, and it's not the case that B on line 9. These aren't inside any other subderivations, which is important because if they were, we wouldn't be able to use them. So now we can get the whole consequent on line 10 using conjunction introduction from lines 5 and 9. We're almost done here. We have assumed the antecedent of the theorem and we've proven the consequent. So on line 11, we can go back to our main scope line and write down the whole conditional using conditional introduction from lines 1 through 10. That's all of the examples I'm going to include in this video. The logic book goes over theorems pretty thoroughly on pages 187 through page 194. The course manual and strategies for derivations document are also really helpful. If you haven't looked at those yet, I definitely recommend it again. For recommended practice, I'm giving you these problems practicing constructing derivations from the logic book. I'll work through all of those in the review video in case you get stuck, need more guidance, or just want to see how I work them out.